Part 1. Good morning, everyone. I'm going to talk to you this morning about signal processing, and in particular, the two main approaches: analog signal processing and digital signal processing. I'm going to look at some of the key advantages of each of them, and also mention the idea of using a mixed approach. As we shall see, a mixed approach is perhaps the best for several reasons, and I want to look at how this works in practice. First of all, however, let me define some important terms. We talk about signal processing, but what do we mean by the term signal? A formal definition of a signal is as follows. It is a function of, or we could say a variable that depends on, one or more other variables called independent variables. This is written as shown on slide 1. Examples of independent variables are temperature, distance, time, etc. As electrical engineers, we are mainly interested in an electrical signal carried by a wire, or perhaps a radio wave. This signal is a function of just one independent variable, which is time. We can plot this function against the time variable, and we get a graph of a waveform. This waveform is the signal, or rather, the form that the signal takes. Now, there are two main types of signal. There are continuous time signals and discrete time signals. In digital signal processing, time can only take discrete values. For example, 1 second, 5 milliseconds, etc. And to show this, we use a small n as a symbol. In this course, we will mainly be looking at signals involving discrete time. But just because the time variable consists of discrete numbers, this does not automatically make the signal digital. If the amplitude of the signal does not consist of just discrete values, then it is still an analog signal, not a digital one. It is only when the amplitude is coded in some form, usually in a binary form, that it becomes a digital signal. So it should be clear that analog and continuous time signals are not two ways of saying the same thing. It all depends on whether or not the value of the amplitude is coded into discrete values. This is an important point, and one which can sometimes cause confusion. It's very important to study signals because they may carry information. It's true to say that sending and receiving information, and then reacting to the information we have received, is fundamental to human life. I have a little story to tell you. This morning, as I was driving here on my way to this lecture, I received a phone message on my hands-free set from my wife. She told me that she couldn't get to work because the car wouldn't start. So I had to go back home, take her to work, and then come on here to the university. That's why I was a little bit late for this lecture. But the point of this story is that it illustrates in a very small way how important messages and signals are in our everyday life. We really couldn't do without them. They're an integral part of living together in groups or as a society. So, to get back to the main part of my lecture, what about processing? What does processing involve and why is it so important? Well, we process signals in order to change them into a better form. Better means more useful or convenient. For example, consider the electrocardiogram, or ECG waveform. The first picture on slide 3 shows what this waveform usually looks like. It's very important that the signal is clear, so doctors can analyze the trace for any problems or malfunctions. But research has shown that the signal can easily be corrupted by noise. For example, the trace can be corrupted by 50 Hz power line pickup from the normal electricity supply. To eliminate this noise, we can use a band elimination filter when the signal is processed. In this way, we can see how signal processing can give a clearer ECG trace. It has changed the signal into a better and more useful form, as seen in the second picture on slide 3. There are 3 basic ways of processing signals. The first way is analog processing. Here, the signal is received and processed in analog form. This was the most common form of processing up until the 1970s. The second way is digital processing. In terms of convenience and accuracy, digital processing is a much better option, thanks to the invention and use of microprocessors. It is usually much cheaper too. The third type of processing is what we call mixed, and this means a combination of analog and digital processing. It could be argued that analog processing is out of date and no longer needed. After all, we have seen that digital processing is much more effective and economical. But it's not that simple. From the point of view of the real world, most of the signals we meet are analog in form, and most of the output that we need is analog. For example, think about telephony. We speak into the phone and generate an analog signal. This can then be converted into a digital signal and processed in various ways. It can then be transmitted and received by another phone in digital form. But we can't listen to a series of zeros and ones. This is the big problem with digital forms. So we need to convert the digital signal back into an analog one, in other words, back into speech. So increasingly we find that engineers use mixed processing for the best, most useful results. And that's what I want to look at in the next part of